Good morning, class, and welcome to this lesson on Magnetism 12, Faraday's Law of Induction. Today we will be able to calculate the EMF for any change in flux. So, if we go back to our last video, we're referencing this picture right here. If there is motion, if there is a velocity of a conducting rod in a magnetic field, if there is motion of a conducting rod in a magnetic field, it'll produce an EMF. It'll produce a voltage and a current. Okay, and we had the equation that the EMF is equal to VBL. This being based on the length of the rod, the magnetic field, and the velocity of the rod in the magnetic field. So this is a very specific situation where the magnetic, we are changing the amount of field lines in a magnetic field. So we're going to go to Faraday's law now. Faraday's law, and we're going to expand on this idea a little bit. And Faraday's law is very simple. The EMF, so same thing, the EMF, and this is going to be our more used equation, to be honest with you, versus this one. The EMF is equal to the negative number of loops times the change in flux over the change in T. Okay, so this is so if we have a loop of wire, or we have multiple loops of wire, this capital N here tells us how many loops are in that wire. Okay, so if there are more loops, we have more of an EMF. Okay, then we have the change in flux here. We have the change in flux, and as you remember, flux is BA cosine theta, and since the change in flux is going to be BA cosine theta minus BA cosine theta, and then delta t is just a change in time. Okay, so as long as something is moving in time, whether it's the magnetic field, the area, or the angle, it's going to produce an EMF. This equation is a little bit better. This equation is a little bit better simply because in this situation before, when we had this equation, we were talking about basically it's the magnetic field that's changing, because as you move it this way, there are more field lines coming through this loop, right? There's more field lines coming through this loop. But as we know, flux is a combination of the magnetic field lines, the area, and the angle between the magnetic field lines and the normal to the area. So this equation right here actually encompasses all changes in flux, because any change in flux, if it's either the angle, the area, or the magnetic field, will produce an EMF. It will produce a current. Okay, and the more loops we have, the more it'll affect it. So this is actually an example. This is a more in-depth equation, and depending on what information you're given in your question, you might need to use this one, you might need to use this one. It all depends on the question. The only thing I want to point out is there is a negative sign here, and this negative sign is really meant for direction. As we talked about before, if I am pushing on this rod, if I'm applying a force, the magnetic field force will go in the opposite direction. The magnetic field force will go in the opposite direction due to conservation of energy. Okay. So that is it for Faraday's law of induction. It's really just a combination of everything we've learned so far in magnetism. We have magnetic flux, and now we have voltage and induced current, induced voltage and induced current. And I just want to point out this answer, it is EMF. This answer will be in volts. This answer will be in volts.